Okay, good afternoon, everyone. And it's my great pleasure to speak at this conference. I want to thank the organizers for inviting me. And also, I want to thank Richard for a very nice introduction of the background of my work. That saves me quite some time. Today, I'm going to introduce a new method for learning the topics from the collection of documents. And this is a joint work with my PhD student. In this talk, I'm going to use two real data sets. The first data set is a collection of Associated Press news articles. And this data set was collected in early 1990s as part of the result from the first text retrieval conference. And here, N is the total number of news articles, and P is the total number of distinct words that are ever used in these documents. The second data set was recently collected by Ji and Jin. And for this data set, the documents are the abstracts of statistics papers published in 4 journals in the past 10 years, recent 10 years. Okay? So for the documents, we're going to use the bag of words representation, which means in our data, we will only record the empirical word frequencies in each document, but disregard, say, the word orders, phrases, grammars. Okay? For example, if document J is a news article with 500 words in total, and the word I, happy, appears 4 times, then this entry equals to 4 divided by 500. Here's a very popular topic model. Okay. We visualize that the data matrix is the sum of a signal part and a noise part. And the signal part corresponds to the expectation of the data matrix. And the important assumption here is that the signal matrix is low rank. So in detail, okay, we recall that the ith column of this signal matrix contains the expected frequencies of all P dictionary words in document I. Okay? And we call a vector the probability mass function on the dictionary if it is a p-dimensional non-negative vector with the entries sum to 1. Okay? So if a topic K is under discussion in this document, and then the expected word frequencies omega I equals to a PMF AK. And for different topics, the AKs are different because when we discuss different topics, we use the word frequencies in the documents will be very different. And it's, in general, it's hardly the case that one document only discusses one topic. And if it discusses several topics, then the omega I, expected word frequencies, is a convex linear combination of the different AKs. Then under this model, we can factorize the signal matrix omega in this form. Please keep in mind that this omega may have a few thousands of rows and a few thousands of columns, but it is low rank. Okay. The problem of interest here is to estimate this topic matrix A. Okay. And this problem is a very important problem in text mining. So once we learn these topics, we can use them to analyze newly given documents, to do fast query, to automatically index large number of documents, say. I need a notion that is widely used in the literature. The quantity of interest A is a tall and skinny matrix, and each row of it corresponds to a dictionary word. Okay? And we call a row of A an anchor row. It has only one non-zero coordinate. The interpretation of anchor words is that these words appear in the documents only when a certain topic K is discussed. For example, a gunshot can be viewed as an anchor word for the topic crime. It won't appear if you discuss sports or climate change, say. Okay. Motivated by the low rank of the signal matrix, today I'm going to introduce a singular value decomposition method for topic estimation. However, the immediate challenge is that the different rows of the data matrix are on very different scales. The reason is that some words appear much more frequently than some other words. For example, in scientific applications, words such as advantage, discovery are much more frequent than words such as happy or sad. So it's desirable to normalize the rows so that they are more or less on the same scale. However, the very tricky part here is that the signal matrix and the noise matrix need very different normalizations. And we found that these normalizations are appropriate. Okay? Before SVD, we add a pre-SVD normalization by rescaling each row by the square root of the average of that row. Okay? We then obtain the K leading left singular vectors of the data. K is the number of topics. Okay? Then we propose using a post-SVD normalization called score. Score is a recent idea developed by Jing in 2015. Okay? To implement the score, we divide each of the second to the K's leading singular vector by the first singular vector entry-wise. These ratios are entry-wise. Okay? By parent theorem in linear algebra, all the entries of psi 1 hat are non-zero, so this is well defined. Okay. And this resulting matrix is still a tall and skinny matrix with k minus 1 columns. In the remaining steps of our method, I'm going to use this matrix R hat to estimate A. Under mild regularity conditions, R hat is very close to its non-stochastic counterpart R. The way we obtain R is that we simply replace the D, the data matrix here, okay, by the signal matrix omega. We then do SVD and we then do the score normalization. That gives R. In the next slide, I'm going to present the main surprise of this work. That is a simplex structure associated with the rows of R. Okay. R is a tall and skinny matrix. Each row is in dimension k minus 1, and it represents a word. Let's say if k equals to 3, then each row of R is a point in dimension 2. Here is the plot. Surprisingly, we find that these rows of R are all contained in a triangle, and the red points represent the anchor words. And you can see that all the anchor words of one topic fall exactly on one vertex of this triangle. And the non-anchor words are in the interior. And this inside generalized to a general K. The rows of R form a data cloud with the silhouette of a simplex. Still, it's unclear how this is related to estimating A. On top of the simplex structure, I have some additional discoveries. Okay? So given the vertices, we can write each row as the convex combination of the k vertices and let pi I denote the unique convex combination coefficients. If we stack all the pi i's together, it gives us this p by k matrix pi. And it turns out that this matrix pi is directly connected to the targeting matrix A using this equality here. So on the left-hand side, this is a diagonal matrix, where the diagonal entries are from the leading left singular vector. This is also a P by P diagonal matrix from the pre-SVD row-wise rescaling. So basically, both of these two matrices are known from the data. Okay? This K by K diagonal matrix is unknown, but it does not matter. Okay? Because this is a diagonal matrix, each column of A is proportional to the corresponding column of the left-hand side matrix. And remember, each column of A is a PMF, and it has to sum up to 1. So therefore, if we normalize each column of the left-hand side by its L1 norm, we immediately recover A. Okay? So this is our main idea. It naturally gives rise to our proposal. We first use the rows of R to estimate to identify the K vertices, say, by looking at the convex hull of the data cloud. We then once we have the vertices, we immediately have the matrix pi and the whole left-hand side. And we then normalize each column of the left-hand side. That exactly gives us A when there is no noise. Okay. So our proposed approach has 3 simple steps. The first step was introduced slightly earlier. In the second step, the main goal is to use the rows of R hat to estimate the K vertices. R hat is a noisy version of R, so therefore we will see a blurred simplex. And the problem is how to estimate the simplex with noise corruption. I will discuss it later. And the third step, once we have the vertices, the third step follow exactly from the inside from the previous slide. Okay. Before I proceed to discuss vertex hunting, it seems that we need to answer a more urgent question. Is the simplex structure we discovered here really supported by the real data? We investigated the Associated Press dataset. Okay? For this dataset, the number of topics K is known, and we tried different K and found that K equals 3 produced the most meaningful results. This is the plot of the rows of the matrix R hat from the data, and you can see a very clear shape, triangle shape there. And for those words that are close to one vertex, they tend to be the anchor words of a topic. And these are anchor words of the topic politics, anchor words of topic crime, anchor words of the topic finance. Okay? So the real data fit our theory very well, which is very encouraging. Now I will introduce the vertex hunting. Okay? Please keep in mind, when we do the vertex hunting, we are dealing with the rows of this skinny, tall and skinny matrix R hat, which means all the data are eventually low dimension, in dimension 5 or 3 or 6. So this cannot be a very hard problem. Okay? After we finished this work, we realized that this problem is related to the literature so-called end-member extraction in hyperspectral unmixing. Most of the methods tend to solve an optimization with the objective being the volume of the simplex. But actually, in our proposal, we used a very simple method, and that works extremely well for the data. The idea is as follows. We first run the classical k-means to these data points, assuming L clusters, and L is a tuning integer. We typically take as 10 times k. Okay? And then the output, these blue dots are the local cluster centers output by the k-means algorithm. And it turns out that these local centers also have the silhouette of the simplex. So in the next step, we'll remove all the original data points, but only keep these local centers. Now the problem is to find a simplex using these 15 or 20 points, which is a very simple problem. Okay? You can exhaustively search to find the best fit simplex. Here are more details. Okay. In vertex hunting, we require that the k vertices of this simplex have to be selected from those L local centers. So we can do it. We can do some exhaustive search or graded search. And the criteria for a best fit simplex is that if this simplex contains all local centers, it is the only one that is the best. Otherwise, we will find the one such that the maximum distance from a local center outside the simplex to this simplex is minimized. Okay, I hope there are no questions for this method. Now I will show you how our method performs. We implemented our method on the 2 real data sets introduced at the very beginning. For the Associated Press data, by choosing k equals to 3, our method estimated 3 topics. And this is a list of anchor words for each of the 3 topics. We can see that these words are very meaningful. For example, for the topic of crime, the anchor words include shootings, injury, marfel, detective, gunfire, aftershocks, etc. Okay? Some words seem to be quite confusing, such as Bangladesh, Hindus, and Dhaka, the capital city of Bangladesh. And then I Googled it, and then I found that in 1990s, so remember this data set was collected in early 1990s. In 1990, there were a series of attacks against the Hindus in Bangladesh. And Wikipedia called it the Bangladesh anti-Hindus violence. I guess that's explained why we see the words here, these words.
How do you know this is 3? K. K could be anything.
That's true.
What did you try k equals 4, k equals 5, and then show you somehow that adds no extra value?
So in theory, you can always estimate k from the square plot of the data. So if you see a large drop of the singular values, you can set that as a k. But in practice, we feel that the best strategy is to first use the square plot to identify a few possible values of k. Then we run the algorithm. The algorithm is very fast, so you can run it for every k. Then use subjective judgment to choose the k. Yeah. Alternatively, we may start from a relatively small K, identify some high-level topics, and then do hierarchically use our method. Yeah. So for the anchor words for the topic politics, many of them are related to the Cold War. For example, you can see the Russians, the politicians such as Gorbachev's, Yeltsin, and American politicians. For example, Sununu, he's the core member of the government. He's a core member of the team of President Bush Sr. And Herbert, which I think refer to the first name of President Hoover. Okay, and also you can see some countries which attracted a lot of attention in early 1990s, such as Cambodia, Afghanistan. Okay, and then for finance, the anchor words are also very meaningful. Okay, you might feel that this word rose is very confusing. Okay, this is not a flower. This is the past tense of the word rise. And in financial news, you always see something like the S&P 500 index rose 70.7 points, say. Okay. And as I mentioned earlier, the real data support our discovery of the simplex structure. And if you look at it more carefully, you will find a very interesting phenomenon. There is a hole here near one edge of this triangle. Okay? Can anyone guess what's the reason for this hole here? If a word is located near this edge, that means this word is related to both crime and finance, but it is completely unrelated to politics. And in early 1990s, it's hard to link for crime and finance directly, okay, without anything with politics. In contrast, we can find many words that are on the other two edges of this triangle. For example, for this edge, you can find words such as terrorist or Nazi that are related to politics and crime, but are unrelated to finance. And here we can find words such as treasury or fiscal that are related to politics and finance, but are unrelated to crime. For the statistics abstracts data, we also tried a different number of K, and we found that K equals to 6 seems to yield the most meaningful results. And if we look at the anchor words by each of the estimate anchor words for each of the topic, it seems that these topics can be nicely interpreted as research areas. For example, for multiple testing, we actually have a talk this morning by Lucas about multiple testing. And you see a lot of words such as family-wise error rate, K family-wise error rate, Benjamini-Kalkberg, false rejection, etc. And for the topic bias, like posterior prior, conjugate prior, improper prior, mode, sampler. Okay. And for the topic variable selection, we also find a lot of words that are very meaningful. So this is my research area, and you can see the penalties, 0, that correspond to sparsity, selection, tuning, lasso regularization. Okay? And the angle corresponds to the famous least angle regression method. And this clipped may come from clip thresholding or from the very well-used non-convex penalty scat. What is very interesting here is the word enjoys. Why does it appear here? And it turns out that the reason is that in a very highly cited paper in this area called Shore Screening, Shore Independence Screening by Fan and Lu. So in the abstract, they said that our method enjoys the oracle property. Then in a lot of in a lot of later articles which cite this paper, they use the same words there. Okay? And then for experimental design, you see the words of different design like Larkin hypercube design, aberration design. Okay? And interesting is that the toxicity appears here because in a lot of papers in this area, their application problem is in toxicological study. Okay? And for time series, you see they are meaningful. And this auction is due to that time series models are used a lot for online auction data. And the last topic corresponds to applications such as in medical science, vaccine, infected, in social science, depression, schools, in climate change, warming, and it seems some of the words are also related to the area of causal inference. Okay.
What is the Rubin? What is the Rubin theory?
I guess it's a Professor Rubin out in the Harvard study. I think this topic may be a mixing of application and causal inference. So there should be some hierarchical structure there, some finer layers there. Okay. For the real data, we don't have the ground truth, and it's hard to compare different methods. So we'll compare our method with other methods using the simulated data. I classified the other topic, matrix estimation method, according to the assumptions they rely on. So in this matrix W contains the weights of documents on topics. So in our model, it's simply treated as unknown parameter. But for the first class of methods, they impose an additional layer of Dirichlet model, probabilistic model on W. Okay, and we have this very famous method called latent Dirichlet allocation, and another is a tensor decomposition method, where they try to match the moments with the whole modeling. So for these type of methods, this assumption is in general quite hard to validate in real data, and also the Bayesian approaches tend to be computationally relatively expensive. For the second class of methods, they are based on a very restrictive assumption that each topic has to discuss each document has to discuss one and only one topics. So therefore, they are only for special cases. And they also use SVD in their methods, but their SVD are used for clustering the document. Therefore, these SVD methods are very different from ours. Our method belongs to the third class. And the existence of anchor words. For the existence of anchor words, we have found a lot of support from the real data. Okay? And what differentiates our method from the other method in this class is that we use SVD. Okay, but they don't use SVD. And SVD yields simultaneous dimension reduction and noise reduction. So we benefit in both computation and in error rate. And in our simulations, we will compare the latent Dirichlet allocation, this method called TSVD, and this method here called anchor word recovery, or AWR for short. Okay. In our simulation settings, we measure the performance of the method using the this so-called L1 estimation error. Okay, and we take the log just for the convenience of for the display purpose. And there are 4 parameters related, key parameters in our setting. P, the total dictionary size. N, the total number of documents. Capital N, the average document length. K, the total number of topics. Okay, and the red line is our method. You can actually see a great advantage of our method. In particular, we found that you see the decreasing curve here. Okay, so this means that our method can effectively take advantage of more and more documents and longer documents. For other methods, we also see some very slight decay there, but because of the log scale, then they are not very, not very obvious. Okay, and we also have many other simulation settings. Now, how about the computational cost? The main computational cost of our method comes from the 3 parts. Okay, so the last 2 parts are from the vertex counting. But please keep in mind, for vertex counting, we are already dealing with very low dimensional data, like dimension 5 or 6. So the computational cost is very low. And the SVD is something that is quite manageable, even for very large scale data. Okay? And we also compare the real running time of our methods and those of other methods using the real data. Okay, so this is AP data. This is another very commonly used data called that consists of NIPS papers. And we use the same K for all the methods for the fair comparison. You can see that our method is hundreds of times faster than the popular LDA, and this another method that relies on anchor word assumption. TSVD is also very fast. However, our error rate is much better. And later we will show that our method is also rate optimal, but the others are not. Now, let me make a summary. So behind our method, there are key innovations. The first is the discovery of simplex structure. Okay? If you are familiar with the topic estimation literature, you will know that a simplex is not something new. Then what's the difference between our simplex and those simplex structures in other words? The difference is that our simplex is associated with the SVD and is in very low dimension. In contrast, this work explores the simplex structure associated with the rows of the original data matrix. And this work explores the simplex structure associated with this so-called word co-occurrence matrix. And these rows live in very high dimension. So N and P can be a few thousands, but our simplex is very low. So it enjoys advantage in both computation and also in error rate, because we deal with low dimensional simplex. Another key innovation is that we use the score normalization in our method. The goal of the score normalization, the role of the score normalization is as follows. So if you do not normalize the singular vectors, just take the original singular vectors and look at the rows, they actually form the data cloud form of simulation cone rather than simplex. It's not clear how to do the vertex hunting. We know that the simulation cone can be normalized to simplex by some way, but the question is that how to normalize it for the how to normalize is non-trivial. Unlike this simplex structure, you can find some trivial ways to normalize it because all the data live in the positive cone, but that's not the case. And here, and the score is actually a very smart way to do the normalization. Okay. Score was originally proposed in this paper, and they found it was very effective for network community detection. Later, in my collaborated work with the author, we extended score to network mixed membership estimation, and today we further use it for the topic estimation. Okay. I hope I have convinced you that our method has some practical values. Now, in the remaining part of the talk, I'm going to introduce, discuss the theory of our method. Briefly speaking, our main contributions are twofold. First, we derived the minimax convergence rate for the topic estimation, and this minimax rate was not known before. Second, we proved that our method is indeed rate optimal, and we found that some other popular methods turned out to be non-optimal. When introducing the topic model, I actually did not mention how we model the noise matrix. To complete the model, we need some background about the multinomial distribution. Okay, so given a PMF on the dictionary, we think the document is generated in this way. So if the document has capital N number of words, then these words are independently drawn, and each of them is drawn from the dictionary using the PMF eta. Then naturally, the word counts follow a multinomial distribution. Just to remind you, in our previous modeling, the signal part of the matrix is low rank. Okay? And now we model the noise part. It's equivalent to model the D itself. And we think that the document counts follow multinomial distribution, where the number of trials equals to the document length, and different documents may have different lengths. And those event probabilities are from the corresponding columns of the signal matrix. Okay. Then in our asymptotic framework, we assume that the number of topics K is fixed. And then we let the dictionary size, the number of documents, and the average document length tend to infinity. We need some conditions here. Okay, this is mild. And for here, this is a very fundamental condition. So if we ignore this logarithmic term, then whenever this assumption is violated, our lower bound shows that no method can do successful topic estimation. So it's very reasonable. This is a very reasonable assumption. And this is mainly for the technical convenience. We don't think it is a bottleneck of our method. And also, we assume that we need a certain amount of anchor words per topic. So here, this is the lower bound for the fraction of anchor words. And using this assumption here, this is a small o1 term, so which means we can allow the fraction of the anchor words to be negligible. Okay, and also we need that the words cannot be very infrequent words. This is also meaningful because in dealing with the real data, we typically first pre-process the data by removing those very infrequent words. Okay. Then we need some regularity conditions. I'll skip this slide. Okay. So I'll jump to our main result. Okay. The loss function we use is this so-called L1 estimation error, and the permutation is due to that you can label the estimated topics arbitrarily. Okay. And our results have two parts. First part, we show that for any parameter settings, the error rate of our method has an upper bound. Okay. In the second part, we show that for any method, there always exists a certain parameter setting such that the error rate has a lower bound. Okay. And the upper bound and lower bound match with up to a logarithmic term, which means our method is rate optimal. Okay. And you can see that the minimax rate is actually a decreasing function of the average document length and the number of documents. And it's an increasing function of the size of dictionary. Okay. And we compared the existing results in the literature. We have not found any method that achieves the optimal rate. Some method can achieve the sharp rate in terms of big capital N and small n, but in general, we have not found any method that is sharp in terms of the rate, the dependence on P. Question?
If you have the Associated Press and statistical articles or abstracts, so what's a typical, how variable is the size of a dictionary?
Yeah. So in the two real data sets we consider, the size of dictionary is a few thousands. The number of documents is also a few thousands. The average document length is a few hundreds. And the topic is determined, the number of topics determined by use is typically no larger than 10 or 15, say. Okay. Then we actually found that there is some fundamental reason for the optimality. So using linear algebra, we actually know that the column space spanned by the topic vectors, topic matrix, and the linear space spanned by the singular vectors is actually the same space. So therefore, you can view estimating the topic matrix as two steps. First, try to estimate the column space of the column space of the topic matrix, and then try to find a k by k matrix to change okay. So first we try to estimate the column space. Then we try to find a certain basis, non-negative basis in this column space. So it turns out that the second part is actually quite relatively easy, and the rate is mainly driven by the first part. And for the first task, we know that SVD is typically the optimal method for estimating the column space spanned by the leading singular vectors. And this was validated in many other problems. Okay, so that partially explains the optimality of our method. And at the same time, it tells us that if a method does not use SVD, it is unlikely that this method will be rate optimal. Okay, and the proof contains some technical ingredients. The first challenge is to deal with this noise matrix. It is a random matrix with weakly dependent multinomial data. I know that here there are many experts in random matrix theory. Okay, so I can tell you for this part, the proof is very lengthy, very messy. But in general, we use standard techniques such as epsilon net argument, such as large deviation bounds for weakly correlated data. Okay, for the second part, we need to develop some new technical tools. So basically, we want to know that if we perturb a matrix, then what's the perturbation on the singular vectors? The famous Davos-Caha theorem, also called sin theta theorem, can quantify the perturbation of the whole singular vector. But that's not enough. We need to carefully quantify the perturbation of each coordinate of the singular vector. Okay? Because the words, the scale heterogeneity is very severe in the data because some words are much more frequent than some other words. So this bounds with change with J. So we need a very delicate analysis here. And I came up with such problem when I collaborated with other people in doing the clustering problem. Then later we further developed these techniques in different papers. Okay. I guess I'm okay in time, yeah. Just to take home message. Today, I introduced the singular value decomposition-based method for topic matrix estimation. So the key innovation behind this method is a low-dimensional simplex structure. And to ensure the existence of low-dimensional simplex and together with some very careful pre-SVD normalization and post-SVD normalization. Okay. What we feel very encouraging is that this discovery of the simplex structure is actually supported very well in the real data, as you see the triangle in the Associated Press. Okay, so I will stop here. Thanks.
In the AP data, you had some points that were even farther than the labor ones. What were those words?
Oh, that's the. I did not check what those are, but I believe that's due to the noise. Due to noise perturbation, you will always see some points that are relative a little farther from the simplex.
This is all done with English. This is all done in English words.
English words.
So say we wanted to do this with Chinese words.
Uh-huh.
Is that a doable?
Yes.
phenomenon?
Yeah. No matter. Okay. Yes, for Chinese words, the difference is that for English, the basic unit of the English language is a word, so it's meaningful. But the basic unit in Chinese language is a character. The character does not have its own meaning. So only when the characters are combined into phrases, we know its meaning. So that means if we just count the frequencies of different characters, we actually lose a lot of information. So I think that's a very good question. I have to check the literature to see whether there are any solutions.
So you mean the simplex is determined by the anchor words, and except for the anchor words, there are other words maybe they have some zero entries, means they are unrelated to certain topics.
Mm-hmm.
Maybe like the happy is not related to crime. So how do this word is represented in your simplex structure?
Yeah, so it appears, so if you plot the R hat, rows of R hat, these rows appear on the edge or face of this simplex, but they not appear on any of the vertices.
I mean, they are, if this word exists, they mean this topic cannot be some certain topics. So do they relies on the outlier of the simplex, or it as another side of the topic vertex?
Could you repeat your last sentence?
If some word exists, it means this article is not related to certain topics. So can you simplex explain this kind of structures?
Okay, yeah. So I try to say it's already incorporated when we it's like those words will appear on these edges. Okay, so they play a role when you try to estimate the triangle.
Thank you, Dan.
Okay, thank you.